Over the rest of this chapter, we look at a final significant real-world issue, and that is speed. It's one way of thinking about it, or rather the amount of computation that is required by these common filtering methods. And over time, I've had a lot of pushback by companies saying, Coulomb counting is really simple, for example, and it takes only a few microprocessor operations, but this common filtering thing is really complicated and it takes a lot of CPU operations. And they're right. Now, part of the complication of the common filter is that it's not all that well understood. There's been a lot of work done on it over the last decade for battery management systems, and I think people are becoming a much more comfortable with the idea of using extended common filters or even sigma point common filters for battery management than they started out. There's a lot better understanding of how they work and what they do and why they work a lot better than Coulomb counting. But it's still true that Coulomb counting is a lot faster in terms of number of operations required than common filtering. So is it worth the extra effort to implement some kind of a common filter? Is it really that much better that I should spend more on a faster processor for my battery management system? It comes down to dollars and cents. Where's the trade-off here? Where's the economic viability that this new method buys? What's the safety trade-off? What's the longevity trade-off? What's the performance trade-off that we gain by having good state estimates versus fairly crude state estimates? So there are challenges associated with addressing those questions. Here, though, over the remainder of the chapter, I want to address the issue of speed. Can we make this method fast somehow? And I'd like to look at, that's not really good English, but look again at this trivial example that was seen before, and we'll see it again. And the philosophical question of this example was, if I have a pack that has only two cells in it, and one cell is fully charged and one is fully discharged, what is the pack state of charge? And we've argued that a pack state of charge cannot be 0%, because 0% would give us the impression that we could add charge to the pack to charge it, but we can't. The pack state of charge cannot be 100% because, again, that gives us the idea that we can discharge, but we can't. And it can't even be the average of the two, which is 50%, because, again, we can neither charge nor discharge. So this idea of pack SOC is not a helpful concept by itself, and we've argued that most times you would want pack SOC, you'd really want energy instead, pack energy, which is completely definable, and there's no ambiguity in what that really means. So this is a straw man, right? This is some kind of an argument that we hope would never happen in practice, and in chapter 5, I think it is, we look at balancing a battery pack so that this would never happen this badly in practice. But in reality, there is going to be some difference between states of charge of all the cells, and it is important to estimate the state of charge of every cell in a battery pack, at least to help with balancing, but also for computing available energy and power and so forth. So there's really good reasons to estimate state of charge for every cell, even in the typical case, and the typical case is that all states of charge are fairly close to each other. And the issue is that running a common filter, especially maybe even a sigma point common filter, is computationally complex. So running a sigma point common filter for one cell is okay. But running 100 sigma point common filters, if I have 100 cells connected in series, is probably not okay. the computation multiplies by linearly by 100, and that's a lot. So what to do? Note that if I've got cells in parallel, they just look like one big cell. So if I've got 100 cells in parallel, I still execute only one sigma point Kalman filter because it looks to the battery management system like one cell. They have a common voltage. But if I have cells in series, they are individually managed. So I would have, if I have 100 cells in series, 100 sigma point Kalman filters is probably too much computation. So in this section, and in fact this section and the next two sections, we're going to talk about an efficient way to estimate state of charge for all individual cells in a large battery pack. And we make an observation that trying to define a quantity that we call pack SOC doesn't make sense. We can define something called pack average SOC, and the key is by adding this word average, we remind ourselves that there is a diversity of SOC among the cells, but we could compute an average of that diversity rather than this term, which kind of says there's a monolithic thing that is pack SOC, and that doesn't make sense. So this pack average SOC can be a useful concept. Why is that? Well, maybe you've already had this argument in your mind, and I will validate this argument. So all cells in a series string are going to experience the same current. That means that we expect their individual states of charge to move in the same direction. If I'm charging the battery pack, all of the cells are going to increase in state of charge. If I'm discharging, they'll all decrease. So they'll move in the same direction and by a relatively similar amount. The difference would be the difference in cell capacities or possibly coulombic efficiencies, but usually that's not the issue. It's usually the capacity that can be different over time with cells as cells age. So even if I start with a battery pack that's completely out of balance, if I charge or discharge for some period of time, all of the cells are going to have their states of charge move in the same direction by about the same amount, but they'll still be different. The window of states of charge will remain relatively the same in the battery pack. So we are going to take advantage of the commonality to help us make an efficient way of estimating all the states of charge. So we will create one algorithm to determine the composite pack average behavior of all the cells in the battery pack, and we will create another algorithm to determine the individual differences between specific cells and that composite average behavior. And this here is really the key. If someone defines a pack SOC against my gut, against what I believe to be true, and they maintain only that pack SOC, they're pretty much doing this. And I've argued that that's not enough. So we're going to do that. We're not going to call it pack SOC. We're going to call it pack average SOC, just to be careful. But we're also doing this step, which is something that's easy not to do, easy to not think of, which is, yes, we're still going to determine all the individual states of charge and all the individual states of all the cells, but we're going to do it in reference to this pack average. And that's actually going to make life simpler. So let's define a pack average state. We'll call it X bar. So this bar notation is often used for an average, so we'll call it X bar. And this XK superscript I, the superscript I is talking about the ith cell. And so I'm summing over I equals 1 to n. You could call that ns, I suppose. We're summing over all of the cells in series of the states, and we're dividing by n, the number of cells in series. So it's just an average. And if one of the components of the state vector is state of charge, like z, z is in there somewhere, we know that every z, 0 is less than any of the z's, so it's less than the minimum of the z's for certain, and 1 is bigger than any of the z's, so it's bigger than the max z for certain. And if I add together, if all the cells are at the minimum and I add them together and divide by n, well, the average would simply be the minimum. And if all are equal to the maximum and I add them together and divide by n, well, the average will be the maximum. But if they vary between the minimum and the maximum, then the average is going to be between the minimum and the maximum. So basically, by a very simple argument, we show that the average state is within the standard range of the individual state, and in particular, the average state of charge is within the standard state of charge range between 0 and 1. So that is a pack average state, which includes a pack average state of charge. Now we can write an individual cell state vector as the state is equal to the pack average state plus an individual deviation away from that average. The deviation is written as delta x, and we call it delta x. And so it's the difference between the state vector, the true state vector of cell I, and the pack average state vector. And all we've done is we've done a mathematical definition that allows us to write any state in terms of a delta and some other quantity. The method we're describing in these 3 sections is called the bar delta filtering because of the x bar and the delta x naming convention. So here is the general big picture idea, and that's about as far as we're getting in this section, and then we'll get into some details and some example results. We are going to use one sigma point Kalman filter to estimate the pack average state, and then we will use n Kalman filters of some kind to estimate the delta states. And this sounds like a lot of work, but let's talk about that later. So here is the single bar filter, the pack average filter. I put in battery pack current measurement, I put in battery pack voltage measurement, I put in the battery pack temperature measurement, and those are all total composite quantities. There's no cell quantities in that at all. And I get a battery pack average, if you will, state estimate. Then I have n of these other filters that are the delta filters. And in these delta filters, I get cell current measurements, which is the same probably, at least in a series string, as a battery pack current measurement. But now I get cell voltage measurements, I get cell temperature measurements perhaps, and I get this overall battery pack state estimate as part of the input to the delta filter. And then the output of all of this is the delta state estimate, and together I have x bar plus delta xi gives me the individual state estimates of all of the cells. That's the idea. It may seem that we've taken a problem that had complexity n. Oh, I could just run 100 different SPKFs. That's complexity n. And it seems like I've replaced it with a problem of complexity n plus 1 because I'm running one SPKF here and 100 of them here, so that's 101 SPKFs instead of 100. It looks like I've taken a straightforward problem, added complexity to it, and made it even harder and slower. But it's not the case. I have added complexity, I suppose, but it's actually faster. And the reason is that the different estimators are not identical in computation. So a single SPKF, the way we've seen it before, is a different complexity from this SPKF, and it's a different complexity from that SPKF. There's three different possibilities here. Now we could say that the bar filter, the pack average filter, is of the same computational complexity, or at least essentially the same computational complexity as the individual state estimators that it uses as a basis. So, what we've seen before, like SPKF. So I've got one of those that is just as complicated as what we've seen before. However, the delta filters, there's so many of these delta filters, but it turns out they can be made very simple. So we can, what looked like n plus 1 is not really n plus 1. This is the plus 1, but this is not really complexity n of the same, n times what we've seen before. It's much, much simpler than that. And we can also notice that while the pack states can change relatively quickly, the delta states change much more slowly because really we're changing based on capacity differences, not on capacity, the absolute capacity of this cell. So the delta states change slowly, so I don't need to update the delta filters as frequently as I do the bar filter. And in the limit, we could update only one delta filter every iteration instead of all n of them. And then, so in iteration 1, I update filter 1. Iteration 2, I update filter 2, etc. And I go through this. And when I've updated all of the filters, then I go back to filter number 1 and start over again. And that can be sufficient because the frequency, the dynamics of the delta states is so much slower. So instead of taking n complicated SPKF filters and updating n of these for n different cells, what we end up doing is we make one SPKF filter for the bar state, the average state, and we have n very lightweight, simple filters that I might update every time instant, or I might not. I might update half of them every time, or a quarter, or even only one of them at every point in time. And so you could say that if this has complexity 1, 1, 1, 1, this is overall complexity n, I'm replacing that with something that's complexity 1, and if I this is a little bit. So overall complexity of 1 plus if I update only one of these delta filters at a time. That's the idea. Big picture. Now it's time in the next section we're going to look at how to implement that idea on an enhanced self-correcting cell model to give you a flavor of what that looks like too.